Dear students, so let us today we start the another chapter called the chemical kinetics. So far we have studied about the structure of the solids, which is mainly studied in inorganic chemistry, and another branch of the science in the physical chemistry, the topic chemical kinetics. You have already studied this chemical kinetics in the PUC levels. Almost the same with little detail you are going to learn in this particular topic. Now you know that the chemical kinetics is a branch of chemistry which deals with the rate of reactions, the factors affecting the rates, and the mechanism of the reactions, and theories of reaction rates. The chemical kinetics is based on the rate chemical reactions can be based on the rate chemical reactions can be classified into three types. Before going to these three types, let us know what is rate of reaction. Rate of reaction is nothing but it is also called the speed of the reaction or the velocity of the reaction. So how fast the reactants they turn into the products is known as the rate of the reaction. Now, as I have told you here, chemical reactions can be classified into three types. One is instantaneous reactions, second very slow reactions, the third reactions with measurable speeds. Instantaneous reactions proceed very fast. Ionic reactions belong to this class. They get completed as soon as the reactants are mixed with the two things or mixed with the other reactant. Example, when silver nitrate solution is added to sodium chloride solution, instantaneously a white curdy precipitate of silver chloride is formed. So this test you will be doing in the practicals. All ionic reactions are fast because the reactions do not involve breaking of bonds as the reactants are already present as ions. The reactions which may take days or even months to complete are called very slow reactions. Rusting of iron which takes place at extremely slow rate in presence of the moisture as well as the air. Between these two extremes, there are reactions which take place at measurable rate. Example, hydrolysis of ethyl acetate to give acetic acid and ethyl alcohol. Another example is the decomposition of hydrogen peroxide to give water and oxygen. Chemical kinetics mainly deals with the reactions which take place at measurable rate because their rate can be measured in the laboratory. These reactions involve breaking of covalent bonds of the reactant molecules and formation of new bonds in the molecule of the product. The bond strength and the number of bonds to be broken differ from reaction to reaction. Hence, the rate of different reactions are different. As I have said, what is the rate of reaction? Rate of reaction may be defined as the change in concentration of any one of the reactant or the product per unit time. I repeat, the rate of reaction is defined as the change in concentration of any one of the reactant or the product per unit time. Consider the reaction PCl5 turns into PCl3 plus Cl2. As the time passes, the concentration of PCl5 decreases and the concentration of PCl3 and Cl2 increases. Therefore, rate of reaction of this reaction we can express in two ways. One is decrease in the concentration of PCl5 divided by the time taken, or increase in the concentration of PCl3 or Cl2 divided by time taken. Since the concentration is usually expressed in moles per liter and the time taken is expressed in either second or minutes or hours, hence the unit of rate of reaction is moles per liter per second or moles per liter per minute or moles per liter per hour. Now let us study the expression of rate of reaction. Consider a reaction R, which is a reactant. It turns into a product P. During the reaction, the concentration of the reactant decreases and the concentration of the product increases. If dx is the change in concentration of the reactant with a small interval of time dt, then the rate of reaction is written as minus dx upon dt. The negative sign indicates that there is a decrease in the concentration of the reactants with respect to time. As the time passes, the concentration of the product increases. In such a case, the rate of reaction will be plus dx upon dt, where positive sign indicates there is increase in the concentration of the product with respect to time. Since decrease in concentration of the reactant and increase in the concentration of the product is a simultaneous process, therefore rate of reaction is expressed as plus or minus dx by dt. For a reaction, A plus B gives P plus Q. A plus B are the reactants, P and Q are the products. In this reaction, rate of this reaction can be given as dx by dt is equal to minus dCA upon dt, which is also equal to minus dCB upon dt. It means decrease in the concentration of A or decrease in the concentration of B. So this is also equal to plus dCP upon dt, which is equal to dCQ upon dt, where this plus sign indicates increase in the concentration of the product P or increase in the concentration of the product Q. Here dCA and dCB are small decrease in the concentration of A and B respectively, and dCP and dCQ represent small increase in the concentration of P and Q respectively in small interval of time dt. For a general reaction, A moles of A combines with B moles of B to form P moles of P plus Q moles of Q. For this reaction, rate of this reaction is given as dx by dt is equal to minus 1 upon A into d into active mass of A divided by dt, which is nothing but which is also equal to minus 1 upon B into d active mass of B divided by dt, which is equal to plus 1 upon P into the dP, that is the active mass of P divided by dt, which is also equal to plus 1 upon Q into the active mass of Q divided by dt. Reaction rates and their stoichiometry. Consider the reaction N2 plus 3H2 gives rise to 2NH3. Here, the rate of the reaction is given as minus active mass of dN2 divided by dt is equal to minus 1 by 3 into dH2 divided by dt, which is also equal to plus 1 upon 2 into active mass of ammonia divided by dt. Above reaction shows that 1 mole of nitrogen combines with 3 moles of hydrogen to form 2 moles of ammonia. If we express the rate in terms of ammonia, it will be double that expressed for nitrogen and 2/3 that expressed for hydrogen. Therefore, rate of formation of ammonia is equal to 2 into d active mass of nitrogen divided by dt, which is also equal to 2 by 3 active mass of hydrogen with respect to time dt. Let us consider another reaction, that is the 2N2O5 gives 2N2O4 plus O2. The rate of this reaction is given as, with respect to nitrogen pentoxide, it is minus 1 by 2 into differentiation of nitrogen pentoxide divided by dt, which is also equal to plus 1 by 2 into dN2O4 divided by dt, which is also equal to plus dO2 divided by dt, because only one oxygen molecule is there. 1 mole of oxygen. The rate of reaction in terms of formation of oxygen will be half that expressed in terms of N2O5 or N2O2, because during this reaction 2 moles of nitrogen pentoxide gives rise to 2 moles of nitrogen tetroxide and 1 mole of oxygen. Therefore, with respect to oxygen, those will be the 2. Consider another reaction, that is 4NH3 gives rise plus 5O2 gives rise to 4NO plus 6H2O. That means 4 moles of ammonia combines with 5 moles of oxygen to form 4 moles of nitric oxide and 6 moles of water. Here the rate of disappearance of ammonia is equal to the rate of formation of nitric oxide, because both have 4. Therefore, rate of formation of water is equal to 6 by 4 times the rate of formation of nitric oxide, that is dNO upon dt. Based on this, let us take a problem. The rate of formation of ammonia by the reaction N2 plus 3H2 gives rise to 2NH3 expressed as the active mass of ammonia with respect to time dt is 2.5 into 10 raised to minus 4 moles per liter per second. What is the rate of consumption expressed in terms of hydrogen as a minus dH2 upon dt? Now, for the reaction N2 plus 3H2 gives rise to 2NH3. It means 1 mole of nitrogen combines with 3 moles of hydrogen to form 2 moles of ammonia. The rate of this reaction can be given as the minus dN2 divided by dt is equal to minus 1 by 3 into dH2 divided by dt, which is equal to plus 1 by 2 into d ammonia divided by dt. Therefore, the minus dH2 upon dt is equal to 3 by 2 dNH3 upon dt. Substituting the value, we get 3 by 2 into 2.5 into 10 raised to minus 4. This is nothing but 3.75 into 10 raised to minus 4 moles per liter per second. Thus, rate of consumption of hydrogen is 1.5 times that of rate of production of ammonia. Coming to the another problem. In an experiment on catalytic oxidation of ammonia, That is, 4 moles of ammonia combines with 5 moles of oxygen to form 4 moles of nitric oxide and 6 moles of water. The rate of formation of nitric oxide was found to be 2.4 into 10 raised to minus 3 moles per liter per second. Calculate the rate of disappearance of ammonia and the rate of formation of water. Now, we know that the rate with respect to ammonia is minus 1 by 4 into d atmosphere of ammonia upon dt, which is equal to minus 1 by 5 the d oxygen divided by dt, which is equal to plus 1 by 4 into d nitric oxide divided by dt. So which is equal to plus 1 by 6 into d water divided by dt. Here, rate of disappearance of ammonia is equal to rate of formation of nitric oxide, because 4 moles of ammonia gives 4 moles of nitric oxide. Therefore, this is equal to 2.4 into 10 raised to minus 3 moles per liter per second. Now, rate of formation of water is nothing but the 6 by 4 into rate of formation of the dNO upon dt. That's equal to 6 by 4 into 2.4 into 10 raised to minus 3, which gives 3.6 into 10 raised to minus 3 moles per liter per second. This is how you must able to find out the rate of the reaction and also the problems based on the rate of the reaction. Now coming to the factors affecting the rate of reaction. This is also very important. The following factors affect the rate of reaction. Number 1, nature of the reactants. 2, concentration and pressure of reactants. 3rd, temperature. 4th, catalyst. 5th, solvent. 6th, radiations or even the light. 7th, particle size. Of course, these things also you have studied in PUC levels. Coming to the first one, nature of the reactant. It is known that inorganic reactions are fast while organic reactions are slow. This is because inorganic reactions are generally ionic in nature, whereas organic reactions take place between covalent molecules. Further, homogeneous reactions are faster than heterogeneous reactions. Consider the 2 nitric oxide reacts with oxygen to form 2 nitrogen dioxide. That is, 2 moles of nitric oxide combines with 1 mole of oxygen to form 2 moles of nitric oxide, and 1 mole of methane combines with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water. Here the reaction 1 is faster than reaction 2. How we say the reaction 1 is faster than reaction 2? This is because in the first reaction only 1 nitric oxide N triple bond O bond is to be broken. Whereas in the second reaction 4 CH bonds, the methane contains 4 single bonds are to be broken. So to break 4 bonds, energy requirement is more. To break the 1 sigma and 2 pi bonds, the energy requirement is less. Therefore, the reaction 1 is faster than the reaction 2. Now coming to the another factor, that is the concentration or the pressure of reactants. Generally, an increase in concentration or pressure of the reactants increases the rate of reaction. As the concentration or pressure is increased, more frequent collisions take place between the reactant molecules, which further increases the number of effective collisions and hence the rate of reaction. I will explain these things in later stage. Coming to the third one, the temperature. The increase in temperature increases the rate of reaction. The rate of reaction becomes double for every 10-degree rise of temperature. Increase in temperature increases the number of effective collisions, and also more molecules gain energy greater than the activation energy. This also you are going to learn in detail in later stage. Coming to the fourth one, catalyst. The presence of a catalyst increases the rate of reaction. A catalyst provides an alternate path for the reaction which has lower activation energy than the original path without the catalyst. These things also you have studied in the lower standards. Coming to the fifth, polarity of a solvent affects the rate of reaction. A polar solvent speeds up a reaction when the product is polar. It retards the reaction when the product of the reaction is non-polar. Come to the sixth factor, that is radiation or light. The reactions which take place in presence of light is called photochemical reaction. These reactions do not occur in the dark. The rate of reaction depends upon the intensity of the radiation absorbed. Temperature does not have marked effect on these reactions. Lastly, the particle size. The rate of reaction increases with decrease in particle size. That's why even in metallurgy, we do the crushing. Crushing helps to carry out the reactions very smoothly. Like this, if you take the smaller particles, the reaction goes more faster than taking the bigger particles. Hence, if any reaction is to be carried out to increase the surface area of the reactants, the particle size should be taken in small. So these are the various factors that affects the rate of reaction. Now let us come to this. Here in this slide I have shown what is chemical kinetics. Chemical kinetics is a branch of science which deals with the speed of the reaction, at what rate the reaction proceeds. So this speed of the reaction can be understood knowing the change in concentration of the reactant or a product in a particular reaction. Here I have shown a graph. So suppose a reactant A turns into a product B. As the time passes, the graph shows that the concentration of A decreases and the concentration of B increases. Therefore, the rate of the reaction is change in concentration of the reactant or the product divided by time taken. Yes, here also I have shown the same thing. That is, as the time passes, the concentration of the reactant decreases, the concentration of the product increases. For this, if you find out the slope gives the rate of the reaction. The slope for the product gives plus dC by dt. The slope for the reactant gives minus dC by dt. Yes, this slide also gives the whatever the things I have explained already. That is, kinetics means the area of chemistry that is concerned with reaction rates. What do kinetic tells us? It tells us about the stoichiometry tells us what and how many reactants or products there are. Thermodynamics tells us if the reaction is energetically favorable or not. Kinetic describes how fast or slow the reaction occurs. We need kinetics to fully describe chemical reaction. Kinetics helps us determine how a reaction occurs and also the mechanism of the reaction. Therefore, we call the rate of reaction as the change in concentration of a reactant or a product per unit time. And here also I have explained the same thing. For a reaction, A moles of A combines with B moles of B to form C moles of C and D moles of D. The rate of this reaction is 1 upon A into delta concentration of A divided dA upon dt, which is equal to minus 1 upon B into the change in concentration of B divided by a small interval of time dt, which is equal to plus 1 upon C into change in concentration of the product C divided by a small interval of time dt, which is also equal to the change in concentration of the product, that is D divided by a small interval of time dt. Yes. So this also you have studied in the lower classes. The first graph shows that the increase in temperature increases the rate of reaction. So this without a first graph, so that is the green colored one, and if you increase the temperature by 10 degrees centigrade, that is orange color, that the graph shows, and the area if you see at the end, so the area also becomes the double. That shows that increase in temperature increases the number of effective collisions. We have studied the collision theory, how a reactant turns into a product. The reactant turns into a product because of the collision of the reactants. So, large number of collisions, they take place during the formation of a product from the reactant. And you have also studied all collisions will not lead into the formation of the product. Only few collisions, they lead to the formation of a product. Those few collisions are called effective collisions. So, increase in temperature by 10 degrees centigrade, the number of effective collisions becomes double. Therefore, the rate of reaction also becomes double. And the second graph, it shows that when a reactant it turns into a product, the reactants will have the X amount of the potential energy and the products have lesser energy than the reactants. We know that every system tries to attain least amount of energy to attain maximum stability. So this graph shows that products have less energy than the reactants. Therefore, the products are more stable than the reactants. Therefore, the reactants, they want to turn into the products. The question arises when the reactant turns into a product. The reactant turns into a product when it attains the energy equal to the threshold energy. every reactant molecule should attain the energy equal to threshold energy. When it attains that energy, then only reactants they turn into the products. Otherwise, reactant will not turn into the product. To attain a threshold energy, we have to supply energy to the reactant molecules. That energy is called energy of activation. Energy of activation is the amount of energy required to turn the reactants into the products. So, the increase in temperature, it makes the reactants to cross that energy barrier. The reactant molecules gains energy and it crosses the energy barrier. That means it attains the energy equal to threshold energy, so that the reactants they turn into the products. So this is also another way to explain how the reactants they turn into the product and how the factor, that is temperature, affects the rate of reaction. Coming to the third graph, this shows that the effect of catalyst on the reaction system. Suppose for a reaction you have not used any catalyst. There the black colored one, the graph shows the reactant should attain the threshold energy, and then the reactants they turn into the products. But when we use a catalyst alters the path of the reaction in such a way that energy of activation gets reduced. So because of the reduction in the energy of activation, large number of reactant molecules they cross that energy barrier, that smaller energy barrier, and they turn into the products. So this is the effect of catalyst on the reaction system. That means the catalyst alters the reaction path in such a way that the energy of activation gets reduced, so that within short time all the reactants they turn into the products. The fourth graph, it shows in the first the reactants have higher energy and products have lower energy. The difference in energy between the reactants and products, they are given out from the system. Hence, the reactions where the reactants have higher energy and products have lower energy, these reactions are called exothermic reactions. In exothermic reactions, products are more stable than the reactants. Coming to the second graph, here the reactants have lesser energy and products have higher energy. Still then the reactant it turns into the product, but the product is not stable because it is having higher energy. And this is a graph for endothermic reactions where energy is absorbed. The first graph shows exothermic reactions where energy is given out. Now coming to the another slide which I have already explained, the kinetic reactions. That is, they are called fast reactions, slow reactions and moderately speed reactions, and chemical kinetics deals with moderate speed reactions. Here I have shown the various reactions and their rate law, how the rate of reaction can be explained. How this rate law can be explained, students, you are going to study this in the chemical kinetic 2 topic. Okay, so this slide is more appropriate at that time. It is not now. Thank you.